Electrical Machine 2 EX501 Unit 1 DC Machine Part 1. In today's lecture, we are going to discuss about the armature reaction effects and various removal methods. There are various detrimental effects of armature reaction in DC machine. Distortion of the main field flux gives rise to three detrimental effects, and reduction in field flux leads to one bad effect: rise in iron loss, poor commutation, sparking are caused by distortion of main field flux, whereas the reduction in field flux influences the cost of field winding. Iron losses. These losses depend on the maximum value of flux density in teeth and in the pole shoes. The armature reaction, by distorting the main field flux waveform, increase the flux density considerably over its corresponding no-load value. As a result, iron losses, particularly in teeth, are much greater on load than on no load. In addition, high degree of saturation in teeth forces the flux to stray into the core and plates, and covers, etc. This all leads to more eddy current and hysteresis loss. Roughly, the iron losses at full load is taken to be 1.5 times its value at no load. Commutation. At no load, zero crossing of flux density wave is along the geometric neutral axis. Under loaded condition of the DC machine, zero crossing of the flux density wave is shifted by an angle theta, which depends on the magnitude of armature current. For good commutation, the coils short-circuited by the brushes should have zero EMF induced in them. The brushes are usually placed along geometric neutral axis. Since zero crossing of the flux density wave is shifted from geometrical neutral axis or Q axis, the coils undergoing commutation do not have zero EMF induced in them. The induced EMF in the commutated coils delays the reversal of armature current in the short-circuited coils. This may result in detrimental sparking or poor commutation at the brushes. Sparking. Under heavy load, the flux density waveform is distorted considerably. If the two coil sides of a coil are under the maximum flux density points, a much greater voltage may be generated in this coil. If this rotational voltage between adjacent commutator segments exceed 30 or 40 volt, a spark may occur between these adjacent segments. Sometimes this spark may spread around the commutator in the form of ring fire. Cost of field winding. Demagnetizing effect of cross-magnetizing armature MMF is to reduce the total flux per pole from its no-load value due to magnetic saturation. In a generator, the magnitude of EMF generated in the armature decreases with increase in load. In a motor, electromagnetic torque is decreased as the flux per pole is reduced under load. In order to compensate for these reduction in total flux, the field MMF must be augmented. This is possible by increasing the number of turns in the field winding or by using thick wire for field winding. Either of these schemes entails more copper and therefore more cost of field winding. Methods of limiting the effects of armature reaction. The cross-magnetizing effect of armature MMF can be minimized at the design and construction stage of a DC machine. Various methods of mitigating the effects of armature reactions are as follows. High reluctance pole tips, reduction in armature flux, strong main field flux, interpoles, and compensating windings. High reluctance pole tips. If the reluctance of the pole tips is increased, then the magnitude of armature cross flux is reduced and the distortion of the resultant flux density wave is minimized. The reluctances of the pole tips can be augmented by using an eccentric pole shoes, also called chamfered. A machine fitted with chamfered or eccentric pole face has short air gap at the pole center and longer air gap lengths under the pole tips. That is, a profile of the pole shoes is not concentric with the armature core as shown in the figure. Another method of increasing the reluctance to cross flux is to assemble alternatively the pole laminations depicted in figure. That is, if the first lamination has the pole tip to the left, the second lamination has its pole tip to the right, the third lamination pole tip to the left, and so on. The third lamination pole tip to the left, and so on, until the required pole depth is developed. Since the iron loss under the pole tips is almost halved, the reluctance under the pole tips is considerably increased. The, the two construction techniques mentioned above reduce the main field flux to some extent. In order to maintain it constant, the main field MMF must be raised accordingly. But the influence of increased pole tip reluctance is more pronounced on the cross flux than on the main field flux. Another construction technique of reducing the armature cross flux is to create more reluctance in the path of armature flux without reducing the main field flux noticeably. This is achieved by using field pole laminations having several rectangular holes punched in them. One such lamination having 4 holes or slots is shown in figure. It is seen that the reluctance offered to the armature flux is increased due to 4 air gap openings introduced in the path of cross flux. As a result, the armature cross flux is reduced considerably, whereas the main field flux remains almost unaffected. Strong main field flux during the design of DC machine, it should be ensured that the main field MMF is sufficiently strong in comparison with full load armature MMF. Greater the ratio of main field MMF to full load armature MMF, less is the distortion produced by armature cross flux. Predominant would be the control of field MMF over the air gap flux. Actually, this ratio depends on the type of duty cycle the DC machine has to perform. The effect of armature reaction in the interpole zone can be overcome by interpoles placed in between the main poles. The magnetic axis of the interpole winding is in the line with the quadrature axis. Interpole winding is connected in series with the armature so that the interpole MMF is able to neutralize the effect of armature MMF in the interpole zone at all levels of load current not exceeding the safe limit. Compensating winding. The effect of armature reaction under the pole shoes can be limited by using compensating winding. This winding is embedded in slots cut in the pole faces of the DC machine. This is the best but the most expensive method